Good morning to all of you. Welcome you guys. Welcome you all. How you are doing, everybody? I think we are live. Yeah, first of all, do comment करके बोलिए ना भैया. Is my audio videos clear to everybody? Comment करके बोलिए. Is the audio video is clear to everyone? Very good morning to all of you. Yeah, first of all, is the audio video clear to everybody? Fine. Sure. Hello. Let's start our discussions. And first of all, a great news to all the aspirants of GATE 2026. So you have a free mock test. With this all-India mock test, you will get to know where you will stand in the all the aspirants who are seriously prepared for GATE 2026. And this the test series, the test which is on today at 9:30 a.m. and 2:30 p.m. Two slots are there. Whichever the slot is convenient, you can attempt that slot. And so ECE 2025 rankers, these are, you can have a look at now. And we already launched the test series for the 2027 2028 के लिए भी हमने launch हो गया, and which is live from December 15th onwards. And so here today onwards I'm starting a new course, that is electromagnetic field theory for 2027 batches. New batches we are starting, and 𝐂𝐤𝐴 batch for 2028. So this is Asha Batch. This is the West Bengal ka electricity department. Crash course is also running. You can have a look at 𝐂𝐤𝐴 batch. And the another thing is UNA. So this is a great AI platform. With this, you can able to communicate with the UNA. So you can have three modes are there. So one is a voice mode and quiz mode and smart summaries. So according to your convenience, you can able to speak with this. You can have you can utilize this thing. So smart summaries. So here if you upload the document, so it will summarize a complete data, will summarize briefly in short and crispy manner. It will explain. And so the test series which is live, and we are offering a 2 subscriptions, so plus wala as well as iconic. प्लस में आपको क्या चीज मिलेगा? टॉप एडिकेटर्स क्लासेस, लाइव डाउट सॉल्विंग, evaluated mains test series, structured courses PDF, live quiz, unlimited access. आइकॉनिक में और क्या मिलेगा आपको? यू कैन सी पर्सनल कोच भी मिलेगा एंड फिजिकल नोट्स भी आपको मिलेगा, राइट. And you can book according to your convenience. You can book your slot. You can directly speak with your mentor. So you can start the serious preparation with the Unacademy to achieve your dream goals. And these are the GATE 2025 rankers from Unacademies. So सबसे पहले the student has been requesting for this topic, that is data converters. Yes, ADC, DAC and the crash course हमने ये topic हमने complete नहीं किया ना, इसीलिए पहले ये topic complete करेगा. इसके बाद हमने कुछ sequential circuits का problems भी हमने discuss करेगा. ठीक है? Yes, so we'll start. So here one by one subject marathon sessions are starting. Maha revision mein. So subjects are starting. You can follow this creative channel. You will get to know. Right. Yeah. First of all, we'll talk about the data converters. A data converters kya is? So tell me now. First of all. So we need to basically the data which we wish to talk about the two types of data. One is called as a analog. The other one is a digital. Analog signal, the other one is a digital signal. They are the two type form of the data we used to talk now. One is an analog form, the other one is a digital form. And this analog signal, so analog signal which is applied to analog to digital converter, which we used to call it as ADC. ADC. What is ADC will do? It will convert the analog signal converted to a digital signal. The output, so we have this as analog signal. The output में क्या आएगा? Digital signal आएगा. Okay. Next, and the digital signal which is processed to digital processor, it will give the output as a digital signal will give. And finally, after that, the signal again, humans can able to detect only analog signals, and so our brain cannot detect a digital signal. Yes. So here in this Maha revision, so we'll focus on the topics what we have not covered in the revision session. Revision session we have taken the logic gates we have completed, and number systems we have completed, combinational completed, sequential completed. So we didn't completed the data converters, we not done. So इसलिए पहले I am doing the data converters, and thereafter we'll see some important questions will be covered. Okay. Right. Now digital signal, and the digital signal which is given, and that it will process digital to analog converters. And we can able to detect my voice signal is there now. What is the form of my voice signal? Which is the analog signal. And this analog signal will be received by the receiver. It will be processed in the digital form. Processed in the digital form. And you are listening my voice at the output case. At the output. So here, what is the form of the signal you are listening my voice? That is an analog signal. So we are not able to detect the digital signal. So we need to convert the digital signal into analog signals. Okay. So here at the transmitting station, we use the analog to digital converter, and at the receiver, at the receiving station, we use the digital to analog converters. Okay. So combinational circuits we have discussed, and today we will discuss the sequential circuits, and problems related to the concept will be covered. Okay. Now, data converters you can have a look at now here. So data converters. We are talking about the first one, DAC, digital to analog converter and analog to digital converter. And so DAC में क्या है? So then input. What the input to be given for the DAC? You tell me now. Here we'll give the input. So this is the digital input will be given. Will be given the digital input. And this output will be taken as what? Tell me now. Analog output. आउटपुट में क्या मिलेगा हमको? एनालॉग आउटपुट मिलेगा. So we have given the digital input, we will get this as output as a digital output मिलेगा. Right. Now in case of any analog signal, so here analog signal which is in the form of what? Tell me now. Which is varies with the time. And so when we did the quantization technique, the analog signal will be converted to the sampling, and quantization will be converted to a digital signal. And so whereas coming to this ADC, and what the input is given, you tell me now. Input is given as what? Tell me now. Analog input is given here, and that will be converted to a digital form. That is converted into a digital form at the output. And this is the two blocks we are going to discuss. Hamara focus is about this block and this block. Right. So, next. Analog to digital converters and digital to analog converters. So here analog to digital converter which is used in the transmitter, digital to analog converter the receiver. First we'll talk about the receiver and thereafter we'll come to the transmitter. First we are talking about the DAC, digital to analog converters. In case of a digital to analog converter, so you can see now here these are the digital 4-bit of DAC we have considered reference signal. And so here we give the digital input is given here. Digital input. And it will give an analog output will use. Then it will use analog output. So any device can able to measure so up to a certain value only, certain maximum value. That is call it as a V reference. Here V reference we used to call now, that is V reference. This is what you tell me now, that is a maximum possible output. Maximum possible output is called as a V reference. Right, so this V reference and which is equal to maximum output V0 maximum. So if you have taken any device, you might be seeing the ammeter 0 to 5 ampere, 0 to 10 ampere, 0 to 10 microamperes. You might be seeing the 10 microamperes what we are seeing, that is a maximum value. That is called as a reference value. That means the device can able to work up to maximum value of what element of here. So that means that is 0 to 10 only it can able to measure. That is called as a V reference value. And this V reference which we used to also call it as the full scale output, which is also called as what element of full scale output voltage. I hope you might be heard these words. V reference which is also called it as what element of full scale. That means the maximum value can be will get full scale reading. Okay. And first we are going to talk about two types of DACs. One is called as a weighted resistor DAC. The other one is a R2R DAC. Weighted resistor DAC. The other one is a R2R DAC. या अभी तक हमने जो डिस्कस किया V reference means what tell me now maximum possible output, which is also called it as a full scale output voltage. Next, resolution. So resolution means what tell me now here the output voltage of a system will be directly proportional to the decimal equivalent, and so then that means so this V naught proportional to decimal equivalent of the input, where this K is a proportionality constant. This proportionality constant which is called as a resolutions. And we can other manner also we can define this as what tell me now this is the maximum non-zero output. So minimum non-zero output of a DAC. Minimum non-zero output of a DAC, which is called it as a resolution. And it is the output of DAC for LSB equal to 1 when remaining all bits are zeros. Now that means what tell me now here when you have taken, so when you have taken some input we have taken, what is the minimum or input I can able to give minimum digital input? Minimum digital inputs, that is 0 0 0 only. This is 1, LSB is 1. When this 0 0 1 is given, we'll get some output will come now. So that output is called it as a, if we got this value as something 0.1, this is the output we got, then this is called as a resolution. Yes, resolution means what will be now the minimum possible. When I have given a very small input will get us some output will come. That minimum output is called as a resolution. And or we can say the other manner, the smallest change in output when the input changes from one input to the next immediate level. Means, for example, I have taken the input, let us say here 0 1 0 1 I have taken. In this case we got some output, we got let us say V1. And what is the next immediate change in the input now? We have 5. The next change we can say it as what I now 6 now. When 1 0 1 1 0 we have, when I have given, we'll get some output will come now. The difference between these two, that is called as a resolution. Then the resolution, that is K, which is equal to what you tell me now here, V2 minus V1. Understood what I am saying? Resolution means when the input changes from one state to immediately next state, that is called as a resolution. Okay. So from this equation we can say now this resolution, it should be equal to what we can say the resolution. A resolution formula. Resolution K, which is equal to what you tell me. This is output voltage. Output voltage by decimal equivalent. Decimal equivalent of input. Okay. So the resolution we can also define as if the output voltage is maximum, then maximum decimal equivalent. Then if we can also call it as maximum output voltage to maximum decimal equivalent of input. Maximum decimal equivalent of input, which is called as a resolution K. Okay, so we can say this resolution in case of maximum output voltage, which we can say this as a so this means V naught max, that is nothing but full scale output na, full scale output by maximum decimal equivalent is 2 power n minus 1. In case of n bits, what I will get to tell me now here, this value 2 power n minus 1. Okay. Next. And percentage of resolution. Percentage of resolution, and which is given as resolution by full scale output into 100. So that should be given as resolution. And what is the full scale output, you tell me now? The full scale output, which is equal to resolution into 2 power n minus 1 into 100. So then will come to be of 1 by 2 power n minus 1 into 100. Okay, percentage of resolution. Now you can see this problem. Find the percentage of resolution if it is a 6-bit DAC and 12-bit DAC. Now, and so what is the percentage of resolution formula we have seen? Percentage of resolution, and which is equal to 1 by 2 power n minus 1 into 100. So here the n value how much now? 6 now. So that is 1 by 2 power 6 minus 1 into 100. And do simplify, so you can see how much will come this value. Check it now, 1.5 will come. Now second one is what element of second bit? Percentage of resolution. How much will come, you can see. Percentage of resolution, that is 1 by 2 power 12 minus 1 into 100. So how much this value? That is 0.024. Right. Next. Yeah, 4-bit DAC, when the input is this much, output is 6 volts. If the binary data is 1100 is applied to same DAC, the output is. As we have seen, the output voltage of any DAC, output voltage which is directly proportional to the decimal equivalent, is directly proportional to decimal equivalent. So that is V naught proportional to D decimal equivalent. So you can see now here, we can write as what element now here? V01 by V02 which is equal to decimal equivalent of first one by decimal equivalent of second one. Yes, so tell me now here, when the decimal input which is given as this much, that means 9 output we got 6 by output voltage V02 equal to D1 is how much? That is 9 by D2 value which is 12. So how much you will get? You can see now we have 3 3s, 3 4, 3 2s na. So from this what will get this output? You tell me now here, which is equal to 8. Next. An 8-bit DAC produce output voltage given as 0.05 volts. Okay. So for the digital input of this much, they are asking to find the full scale output voltage percentage of resolution. You can see first of all, the number of bits are given as 8 output voltage. See this thing, for the what is the digital input is given now, only LSB is 1. LSB is 1. The output corresponds to LSB 1 is called as a resolution. So from this, can you tell me now this output what they given? That is nothing but what? Tell me now, resolution only na. That is resolution how much? 0.05. Okay. And full scale output, the number of bits are given. How many given now here? 8 bits are given. So what is the full scale output? You tell me now. And which is equal to, yes, resolution into 2 power n minus 1. So we'll get the full scale output voltage, which is resolution is 0.05 into 2 power 8 minus 1. Simplify and get it. How much will come? So this value which will get it as 12.75. Next. And they asked to find the percentage of resolution. So this we got it as in. Now what is the percentage of resolution formula? Percentage of resolution, that is given as 1 by 2 power n minus 1 into 100. So that is given as 1 by 2 power, how much you tell me? 2 power 8 minus 1 into 100. So simplify, how much will come? So which will come to be 0.392. I think you can do calculations. Now output voltage we need to get now here V0. So here V0, which is equal to what? Tell me now. So here resolution into decimal equivalent. And what is the resolution? Resolution into decimal equivalent. Now simplify this thing, resolution, which value will come to be given as 0.05 into decimal equivalent. How much the decimal equivalent value? Tell me now. For this one, which will get as what? Tell me now here. 0, 1, 2, 3, 4, 5. 2 power 5, 32, 32 plus 8, 40, 42. How much this value? 42. So you can see this thing, how much this V0 value? Tell me now here. So that is 2.1 volt. Next, draw the output wave of DAC. The corresponding to DAC, they ask him to draw the output waveforms. Now you can see now here they given this as a 3-bit up counter, and so the output is given to a 3-bit DAC. So what will come, you can see if we draw this tabular form, you can observe here. We can use the clock, and thereafter we have this output of a up counter. Next output this corresponding to DAC, and we'll get this output. Yeah, you tell me now what we have. Tell me now clock and then 3-bit up counter. So this will come to be a what? Tell me now Q2, and this is Q1, and that is Q0, and D2, D1, and D0, and this output voltage which is V0. Check this thing, all of you. Now, and we'll see this thing here. When initially we'll consider this as the counter value zeros. Okay. Now this corresponding they connected here, so these values are connected like this. Yeah, what is this output voltage means? What tell me now here? So this is K into decimal equivalent na. Decimal equivalent is 0, so this value 0. When we apply the first clock, that is 0, 0, 1. So tell me what will come. So 0, 0, 1. So will come it as K value 1. So output voltage is 1. Right. And when you apply this as, so now let us say second clock. So this is 0, 1, 0. 0, 1, 0, which will come to be a 2. Next third clock, 0, 1, 1, 0, 1, 1. So this is 3. And the fourth clock, 1, 0, 0, 1, 0, 0 will come it as 4. And fifth clock, 1, 0, 1, 1, 0, 1 will come it as 5. Sixth clock, 1, 0, 1, 1, 0, they will get 6. Seventh clock, 1, 1, 1, 1, 1, 1, so this is 7. Eighth clock will become counter will reset now, then will come it as 0, 0, 0, 0. Next ninth clock 0, 0, 1, so 0, 0, 1, 1 will come. Again will rises after that. So you can see the things now. If you draw this waveform, so you can see now here we have taken x-axis, we have taken clock, and y-axis we have taken as output. Now you can see now first clock, so this is 0. Next we can say this as 1. Next we have 2. Next we have 3. This is fourth clock and fifth clock, sixth clock, seventh clock, eighth clock, ninth clock. So then first clock we have initially 0. First clock it will suddenly will rises to what element? 1. Next up to second clock it is 1 only. Second clock will move to 2. Next third clock it will come to 3. Next fourth clock it will be like this, and fifth clock will get 5 now, and sixth clock will get 6. Seventh clock will come 7. Now 7 we got. Now thereafter what happens? You tell me, after reaching this in 8th clock what happens? 8th clock what happens now here? It will, the moment 8th clock will came, so immediately it will fall down completely. Its value will become 0. 8th clock will become 0, and this 9th clock which is like this. Again, so here ninth clock again will becomes 1. This process again the same thing will be repeat like this. It is a periodic sense. So we have 1, so this is 2, 3, 4, 5, 6, 7. Like that it will come like this. The staircase function we have. Right? Next. Take this problem. Find the output voltage of DAC. They given gray code converter. They given, so binary is the input, so they given gray code converter they applied. So you tell me now what will come this output now, tell me. First of all, they given this as binary code is given now, and binary value given as 1 1 0 0 1 1. So first we need to get the corresponding gray code we need to get. So tell me now how we'll get the gray code for this thing. So MSB as it is will write, and we should find the these two XR now will come it as 0. Next XR between these two is 1, and these two XR which is equal to 0, and these two XR which is 1, these two XR which is equal to 0. Okay, so this is a gray code. So this is the output here. We have 1 and this is 0, 1 0 1 0 will come. Now they connected some NOT gate connected. So that's why this value which is equal to 0 0 1 0 1 1. Now for this we should get this output voltage V0. And what is the output voltage which is given as resolution into decimal equivalent. D I am calling decimal equivalent. So what is this V0? Resolution is how many bits you see? 6 bit now. So this value V reference is given, so that is 10.5 by, so that is 2 power n minus 1 into decimal equivalent is how much? We have this number. So this value how much now? 0, 1, 2, 3, 4, 5. 2 power 5, 32. 32. Okay, this is 0 now. So this value given, this output is what I'll be out. So this is 11 only. Decimal equivalent is 11 only. So this is V0, which is equal to how much now here? 10.5 by 2 power 6 minus 1 into 11. Simplify, get this value, how much will come? That is 1.83. Check this value. Next. Yes, the similar kind of problem has been repeated. So that's why we are doing that variety kind of problems. You can have a look at now. Try this one. The similar kind of problem what we have seen earlier. And we are forming one tabular form. This is a 3-bit up counter. So this is the clock. And this is a up counter. Here which is given to a 4-bit DAC. So we have this is up counter Q2, this is Q1 and that is Q0, and we have D3 and D2, D1 and that is D0, and this is output voltage. Yes, so here we need to draw only the output voltage which is equal to what we can say now here, that is resolution into gain into decimal equivalent. If we see this thing here, these terms are remains constant only. Okay, so that means we need to find only this thing only now. Only we need to focus about output voltage proportional to decimal equivalent. We can write as what element from this? Output voltage proportional to decimal equivalent. So that is V0 proportional to D, we can write simply. So let's see this thing here. When we apply initially clock now here 0, so that is 0, 0, 0. So you tell me now 0 and this is connected to ground. So we have of course output value 0. Right. When we have given first clock, we have 0, 0, 1, 0, D2 is connected to ground. So this is 0, 0, this is 1. So this is 1. Yes, something constant into will get is like if we have taken this as something K, KD, so we can take it as some constant, we can take simply K. If we apply the second clock, so this is 0, 1, 0, then will come it as 0, D2 connected to this is, so this is 0, will come it as 2K. Next third clock 0, 1, 1, 0, 0, 1, 1, so this is how much now? 3K. If we are given fourth clock 1, 0, 0, 1, 0, 0, 0, then how much will come? This is 8K will come, isn't it? Now if we have given 5, so this is what element of 1, 0, 1, 1, 0, 0, 1, so this is 9K. If we have given this as sixth clock 1, 1, 0, 1, 0, 1, 1, so it will come to be what element of here? 11K. See 0 only, no? Then it is 10K. This is 7th 1, 1, 1, so this is 1, 0, 1, 1, then it is 11K. And 8th clock will be counter will reset now. Then will come it as 0, 0, 0. So then again 0. 9th clock 0, 0, 1. So 0, 0, 0, 1. Again will come it as K. Like that will continue. From this we can observe the what will be the output, you can see. We can observe easily the output. Now tell me how much. Option B. Right. Next. Now you can see this one. Find the output after 10th clock. Output after 10th clock if the initial state of the ring counter is given as like this. Initial state of the ring counter given as like this. And here tell me now, initial state of ring counter is given something. They ask him to find the output after 10th clock. They ask him to find. So you tell me now here. So this is ring counter working, we know now. Ring counter, how these functions you can see. Right, so this is, if I say clock initially, so this is Q3 and this is Q2, the Q1 and this is Q0. So here initially when the first clock, that is 0th clock, initial state is given 0 0 0 1. First clock we apply this as 10th clock 2 3 4 5 6 7 8 9 10 clocks we applied. Tell me now, first clock, this is 1 0 0 0. Second clock 0 1 0 0. Third clock 0 0 1 0. Fourth clock 0 0 0 1. Fifth clock 1 0 0 0. Sixth clock 0 1 0 0. Seventh clock 0 and eighth clock 0 0 0 1. Ninth clock 1 0 0 0. 10th clock this much. Okay. We will get like this now. Now you see this thing here, this Q0 they connected to here. This is the clock for this 3-bit up counter. So you see how many times the Q0 is 1. You see here this thing now. Okay, first one we don't need to consider, here onward. First clock onwards we need to see. So how many times now here? 1, 2. That means 2 clocks are given to this thing. So this counter will get incremented by 2. Up counter now initial values we can take 0 0 0. So it will go to 0 1 0 now, 2 clocks. Next Q1. How many Q1s you see this thing? This also 2 clocks only, 2 times only 1. So this also 2 clocks only. This is a 4-bit counter, 0 0 1 0. Next this one Q2 1 2 3. 3 times is 1. So here 3 clocks are going. So then it will become 0 1 1. And this one 1 2 3. This also 3 clocks. That means this value 0 1 1. So we can see now what is the final output now here. They given k value given as 1 given, isn't it? So what is the decimal equivalent here? You see decimal equivalent, which is equal to 0 1 0 0 0 1 0 0 1 1 0 0 1 1. This is the decimal equivalent, right? Now what it is the decimal, this value, how much now here decimal equivalent of this value? That is 4403. Check this thing. So finally we got this V0 equal to what? Tell me now, K resolution into decimal equivalent. So we'll come it as V0 is equal, this is 1 milli na. So if we multiply this thing here, 4.403 volts. This is the output voltage. Next, let's see the another problem similar kind. Now look at now. Here they ask you to find that 20 class they ask you to find. Earlier they given it as a 10 clocks, but it is at 20 clocks. Another thing is here they given up counter, down counter is also given. So you see this thing here. How many times the process will happen, we need to be careful. So here V0 we need to find. So initially what they given? Initial state is given as this much, 0th clock. So at the 0th clock we have the state. We can say this as Q3, Q2, Q1 and Q0. This value 0, 0, 0, 1. Okay. Next, first clock, what happens? You tell me now. 1, 0, 0, 0. Second clock, what happens? 0, 1, 0, 0. And third clock will becomes 0, 0, 1, 0. And the fourth clock will becomes 0, 0, 0, 1. This thing clear now? First of all. Now you see this thing. How many clocks they given are 20 clocks in this. So here if you observe, this 4 clocks is happen like this. 20 clocks means each thing is repeated by 5 times. Each thing is repeated by 5 times. Yes or no, tell me. 5 times will repeat. That means totally here how many are there, you see how many times the output, each bit is 1. So 5 times is 1. So means for this one, this value 5 times is 1, this value 5 times, and this value 5 times, and this value 5 times. Okay. Now you see this thing. This is a 3-bit up counter. 3-bit up counter. So which will be given as, so this 5 times is 1, this value will come it as 5 clocks gone. So that is 1, 0, 1. 5 clocks now up counter. And this is a 4-bit down counter. Okay, down counter 5 clocks. Down counter, so means what is the, when the first clock, when you apply all the values are 1, 1, 1. Next, second clock, so 1, so this value, so you can see now, you can write in the decimal form, you can write first will come it as 15, next 14, next 13, next 12, okay, next 11, and next will come it as 10. So this is 1, 2, 3, 4, 5. 5 clocks means for 11 will come now. 5 clocks means 11. So that is what, tell me now, 1, 0, 1, 1. Okay. Next, this 3-bit down counter. 3-bit down counter, first will come, first clock 7 will come. Next we have a 6. Next we have a 5, 4, 3. 1, 2, 3, 4, 5 clocks. 3 means 0, 1, 1. This is a 4-bit up counter. Up counter means 5 clocks gone now. 5 clocks means what, tell me now, it will come to be a. So 5 will come. So this is 0, 1, 0, 1. Okay. Now what is this output we have given? So this value, so this is decimal k into decimal equivalent. And what is this decimal equivalent value, tell me how much? And this is 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1. This is the decimal equivalent. How much this value will come? How much this decimal value? K value is a 1 milli given us, so that is 10 power minus 3, and decimal equivalent is how much? 11701. So will come to be a V naught value how much now? So 11.701 volt. Got it. Next. Now they given Johnson counter. Johnson counter. We need to find this output. Try this one. Yes, resolution not mentioned, so assume this as resolution is something K. We have given a clock, and this is Johnson counter and DAC, and this is final output. Okay. First, clock and Johnson counter, so that is Q2, Q1, and that is Q0, and D2, D1, D0, and that is V0. Yeah, you can tell me now here. Initially, first clock when you apply, all the values are reset now. 0, 0, 0. So this also 0, 0, 0. This value 0. When you apply the first clock, when you apply, see what happens. And will commit as what, tell me. So this is will commit as 0, 0, 1. Okay. 0, 0, 1. And what will come here? This is, and Johnson counter functioning we know now. This is given as what, tell me now. So if I say this is Q3, Q2, this is Q1, and that is Q0. We are not gate which is connected. We are not gate is connected now. So this value 0, 0, 1 will come it as something K. Second clock, what will come here? sorry, this one, this is 1, this is 1 0, this is 1 0. Now that means this is the 4k will come it as 4k. Okay, next will come it as 1 1 0, so it will be 1 1 0, it is 6k. Next third clock 1 1 1, 1 1 1, so this is 7k. And fourth clock 0 1 1, so 0 1 1 will come it as 3k. And fifth clock will come 0 0 1, 0 0 1, so this is k. Next we apply the sixth clock, so 0 0 0, 0 0 0 will come it as 0. Like this will continue. Seventh clock 1 0 0, 1 0 0, so this is 4k. So this eighth clock 1 1 0, 1 1 0, this is 6k. Okay. Done. So from this we can write the things now. Got it? Now you can see now initially first clock we have 0, next 4k, 6k, 7k, thereafter decreasing. So from this we can draw this thing, roughly we can draw. Tell me now how it could be, tell me. So initially first clock which we have a 0, okay, 0th clock. Next we have a 4k, and thereafter 6k, second clock, this is 6k, and thereafter we have a 7k, this is a 7k, and thereafter 3k, so means it will falls below 4k now. Next it will falls to 1k, and finally will become 0. And the same process will repeat for remaining clocks also. Okay. Right. Chalo, let's talk about the next one. This is op-amp. Right, op-amp. What is this op-amp? You can see now here. And this op-amp. Op-amp is, we are talking about this op-amp which is an ideal op-amp only. Op-amp, our op-amp is, what type of op-amp is an ideal op-amp only. So for this ideal op-amp will have some characteristic. The characteristics of ideal op-amp which is, so the input impedance of ideal op-amp is infinity. Input impedance is infinity. That means no current will enter. And another most important one, outputs of this op-amp will lies between minus VSAT to plus VSAT. It can never be more than that and never be less than that. Okay. So another thing is the concept of virtual ground. What is the concept of virtual ground is? virtual ground is what? Tell me now here. If we are talking about this voltage, I'm calling it as VA. And this voltage, if I'm calling it as VB. And this voltage at the positive terminal, negative terminal, both are equal. So that means here VA and VB, both values are equal. That is a virtual ground concept. And here this is called as a negative terminal. And what it is? This is called as a negative terminal. And this is the negative terminal. Negative terminal, which we used to call it as a inverting terminal. This is called as what element of inverting terminal. Inverting terminal. And this is the positive terminal, which is called as a non-inverting terminal. Non-inverting terminal. Okay. Inverting terminal, the other one is a non-inverting terminal. Okay. Right. And this op-amp has so many applications, but we'll talk about the application which are required for us. So the first thing application is op-amp in an inverting mode. In inverting mode, the amplification and the gain, we can say. Gain in case of a inverting mode. Inverting mode means what? Here supply voltage which is given to inverting amplifier. So that's why this is called as a inverting mode. The gain, which we used to call it as a G, which is given as what? Tell me. Output voltage by input voltage. Output voltage by input voltage, which is given as, that is minus of RF by RI. So this is RF, this is RI. The gain in case of inverting mode, which is given as minus of RF by RI. In case of non-inverting mode, so here this is a positive non-inverting terminal. Now we have given the input, we have given to non-inverting terminal. That's why this is called as a non-inverting amplifier. In this case, the gain, in this case, gain G, which is given as output voltage by input voltage, which is given as 1 plus RF by RI. This is RF, this is RI. Okay. Next, comparator. So op-amp will behave like a comparison of the input signals. If I call this as VA, VA is the positive terminal, VB is a negative terminal. So what happens now? How it will be comparators here? If VA greater than VB, VA greater than VB, then this output voltage, which will come it as plus V saturation, plus V sat. And plus V sat means what terminal? Logic high. That means will come the output as a logic 1 will come. And if VA, that means positive terminal voltage, which is less than negative terminal voltage, then this output voltage, which will come to be a minus V sat. That is minus V sat. And this is called it as what element of logic 0. Okay. In case of a comparator, working is like this. Next, and it will behave like an integrator also. And integrator, how it will behave, so you can see now this is the output voltage V0, which is equal to minus 1 by RC, minus 1 by RC into integral of VI into dt. Okay, minus 1 by RC VI into dt. Okay. Hmm? सो गया क्या किया अभी तक? Okay. Next, in this case, let us talk about the binary weighted type DAC. Binary weighted type DAC. So you can see now in this case, here we have a V reference. V reference, there is a maximum value which is connected. And you can see now if I connected this thing, in this case, binary weighted type DAC, the output voltage V0, the output voltage which is equal to what element of V0, which is equal to 𝐂𝐤𝐬𝐷. What is this thing? Tell me now. 𝐂𝐤𝐬𝐷. What is K is a resolution. And the resolution, this is what type of DAC? Weighted resistor type DAC. Now in this case, K, the resolution which is given as V reference by 2 power n minus 1. And G is what element of gain. Here gain is what element of input is given to which terminal you see? Negative terminal. Negative terminal means what? Tell me. Inverting terminal. Inverting terminal gain is what? That is minus of RF by R. And what the D is a decimal equivalent. D is a decimal equivalent. Okay. And here another important thing you need to remember here, and which is the LSB, which is the MSB here. So LSB resistance here, LSB resistance which is equal to 2 power n minus 1, 2 power n minus 1 into MSB resistance. MSB resistance. Okay. Completed. Now you can see now here. Now you can see in this case. What is the V reference, you tell me now? In this case, V reference which is equal to 5. Okay. So here this is the MSB. MSB resistance is 1. This is the LSB. Here this is MSB and this is LSB. High resistance is LSB. Low current, high resistance. So this means here we can say this as B3, this is B2, B1 and that is B0. So how much this value, tell me now, B3, B2, B1, B0. This is 1, 0, 1, 0. This is 10. Decimal equivalent is 10. Yeah, we'll cover it. So from this decimal equivalent which is equal to 10 and then R value which is equal to 1K and feedback resistance RF which is equal to how much now, 8K. Then how much we can say now, V0 value, tell me now. V0 value which is equal to what, 𝐂𝐤𝐬𝐿 na, 𝐂𝐤𝐿. So that is V0 which is equal to V reference by 2 power n minus 1 into G is a inverting amplifier. So that is minus of RF by R into D is a decimal equivalent. And so you can tell me now what will get the V0 value from this. What will get the V0 value? V reference. Now V reference will come to be a what? So 5 by, that is 2 power 4 minus 1, that is 3, and V RF, that is 8 by 1 into decimal equivalent is 10. So simplify, how much will come the V0 value? How much? Minus now, so we'll come it as 8, that is minus 50. We'll get the minus 50 will come now. So will it be the correct answer? We know the output voltage should be always less between minus V sat to plus V sat only. If this is minus 50, so it cannot happen. So that means what is the value, tell me now? So that's why V0, it should be taken as minus 15 volts only. So minus 50 is wrong. Okay. Right. Now you can see now R to a ladder case. In case of R to a ladder, so we have n minus 1 R resistors, n plus 1 2R resistors are there. R to R. Here, so here we have one extra 2R resistance, grounded extra 2R resistor is there now. Whichever the bit which is near to extra 2R, that is LSB. right? So this is LSB, and so the other side, which will be obviously MSB. Okay, right? So in this case, what is Vx value? So here, so we are not doing the derivation here. Vx will come to be a V reference by 2 power n into d will come. Vx value V reference by 2 power n into d. Right. So now you can see now based upon according to the type of amplifier, the output value will changes. Here in this case, input is given to which terminal? Non-inverting terminal. So that means here if I call this value which is equal to Vx, then this output voltage which will come to be what terminal? 𝐂𝐤𝐷, like earlier we have seen. V naught. So where K is what, tell me now? Here V reference by 2 power n, and G gain. This is what type of amplifier? Non-inverting amplifier. So that's why 1 plus RF by R. Okay. And the D is a decimal equivalent. Next, here in this case you see this is what amplifier? Inverting amplifier. So inverting amplifier also output voltage V naught, which is equal to what term of 𝐂𝐤𝐷. So what is this K, you tell me? K tell me now. V reference by 2 power n, and G is the gain. Gain is how much? Gain which is equal to how much will come? And that is output voltage by input voltage. How much is output voltage by input voltage will come? This value. So this is the gain. This is inverting case minus RF by R. RF by R will come. And D is the decimal equivalent. Now see this problem in this case. And this is what you tell me now. First of all, this is also R to R only. In this case also what we can say now? Gain. So that is case output voltage, which is equal to V naught, which is given as 𝐂𝐤𝐷. Kg into D. And what the K is? V reference by 2 power n. And G gain. Inverting amplifier now, so that's why R, so gain is minus RF by R, and D is a decimal equivalent. Next, here tell me in this case, find the output V out and I. Yeah, you can tell me now first output voltage V out. V out in this case, V out equal to 𝐂𝐤𝐷. 𝐂𝐤𝐷. Here, this is LSB here. And so this is MSB. So here this is, here we have this as B3, B2, B1, and this is B0. And so that is 𝐂𝐤𝐷. K value how much? Which is equal to V reference by 2 power n. V reference is how much? 10. 10 by 2 power n. How many bits? 4 bits are there. 2 power 4. Which is equal to 10 by 16. G, which is equal to what? Tell me now. Gain. This is what amplifier? Yes, inverting amplifier. So that's why minus of RF by R. RF is 10, R is 10. So we'll come it as what? Tell me now. Minus 1. And the decimal equivalent? This is 0, this is 1, 0, and this is 1. So we have 0, 1, 0, 1. So the D value, how much we can say now? This is 5. So we'll get this output voltage V0 equal to K. K value 10 by 16 and G value minus 1. D value 5. You can simplify and get this answer. 2 5s, 2 8s. So that is V0 equal to what? Tell me now. Minus 25 by 8. Okay. Got it. Done. And if you talk about this current, so then how about this current? To tell me now this current, which current? This current is I will go. Then what I can say, this direction we have this as I by 2. And this current is I by 2. Again this current is I by 4. This is I by 4. Equally will divide. This is I by 8. This is I by 8. And this is I by 16. So this I value how much? So if I call this is Ix, if I call I by 8. So how much is Ix value? Which is equal to I by 16. Sorry, not 8 now. So this is by 16. So how much will come? This value Ix will come to be I by 16. So how much this I value we need to get now first? Equivalent resistance. How much this value? Tell me now. R. So this value will come to be a 10K. So this is Ix will come to be a what? Tell me now here. I. So this is 10 by 10K by 16, which will come to be 1 by 16. 1 by 16 now. 1 by 16 milli. Equivalent resistance calculation you understood. So 20, 20 parallel will becomes 10. 10 and this is 20. Again 20, 20 parallel 10, 20. Again 20, 20, 10. Again 20, 20. Overall will become 10. Right. You can see now here. A digital to analog converter with a full scale output voltage given as 3.5 has a resolution close to 14 millivolts. Its bit size is. They ask you to find the number of bits. What should be the number of bits, sir? Now you tell me now basically the resolution which is given as and full scale output by 2 power n minus 1. Now you can see now here 2 power n minus 1 which is equal to full scale output voltage by K is a resolution. How much the full scale output you tell me now? They given us 3.5 by 14. 14 into 10 power minus 3. So simplify, how much will come to power n minus 1? 14. We have simplified, how much will come? And this value will come to be at 250. So this is 2 power n minus 1. I can say 2 power n is equal to that is 251 means which is close to 256. Na? So this means we can say n value that is 2 power 8. Nearly 2 power 8 we can say na? Number of bits close to 256. Next, a student has made a 3-bit binary down counter and connected to a R2R ladder type DAC. Okay, so as shown in the figure, to generate the staircase waveform, the output HUD is different as shown in the figure. He want to generate a 3-bit binary down counter, okay, having certain gain. Okay, so but the thing is he got the waveform is differently he got. Is this waveform is visible to you properly? Waveform, I will draw it, you can have a look at. This is the waveform. Okay, this is the waveform they given. Now you tell me now. He want to get it as basically the waveform as what? Tell me now we should get the down counter. Down counter means what are we now? 7, 6, 5 like that has to be come. But here what happens now? First clock, when you apply first clock we have 7. Okay. Next clock we got 3. Next clock we got it as 5 like this. Why it is happened like this? We need to analyze it. Now first of all let's see what is the output we should get now. Basically you see and so this is clock, we have this is Q2, Q1 and that is Q0, and what is the output they given, output we should get, and what is the output they given from the figure. We need to identify this thing. So you can see, so when you have given 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 clocks if we have taken. Tell me now down counter. So initially values are 0. Down counter will come it as what? 1, 1, 1. 1, 1, 0, 1, 0, 1. So down counter has to decrement now. 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. So 0, 0, 0 will come. And what is the V naught? What is the V naught? V naught will come, you see, that is 0. Now we have, will come it as 7. 7 into kg we can say. That is 6 into kg. 6 into kg. Now we'll get it as what will be next? 5 into kg. 4 into kg. 3 into kg. Then 2 into kg. So this is 1 into kg. Like this will come. Now figure, for the figure what we have, tell me now first, when the first clock we have a 7. They given this is, you can find this as 7. Next second clock we have a 3. Next here we are getting it as a 3 we are getting. Next we have a 5. Next we have a 5 only. Next we have a 1. 1. Next we have a 6. Next we have a 6. After that 2 we have. Then we have a 2. Next we have a 2. Then after 4 is there. And thereafter 4. Now you tell me now why we got like this. Actually we have to get this thing we should get. But we got these things we have. Why it is happened like that, that we need to analyze it. You see this thing 7 means 1, 1, 1. So fine. So 6 we have to get. 6 means how it will come? 1, 1, 0. So this is what element of Q2, this is Q1 and that is Q0. This is 7, this is 6. Now if you see this thing here from this direction, if you see this is MSB 6, but this direction if you see this will be a G3 will come now. Then this will come to be a 3, isn't it? Then it will come to be a what, tell me? Now it is, here we will get it as what element of 5. 5 will be in both the directions will appears to be same only 5. 5 will appears to be both the directions will be 5 only, no change. Okay. Next 4. 4 is what element of 1, 0, 0. This is 4. We see this direction that is 4. But if we see from this direction will be come to be a 1. So from this what we can say here, you see they has interchanged the MSB LSB connections. So here what we can, the connections from the counter to DAC is not proper. So here MSB LSBs are interchanged. That's why we got this as output. Okay. Done. Next, now let us talk about the analog to digital converters. The first we are talking about the counter type A to D converter. Counter type or digital ramp we used to say. Now let's see the working of this counter type A to D converter. Here we have given some input. Let us say the analog input which we have given it as a something 6.2 volts we have given. Let us consider. So first here this will behave like a comparator. Initially the counter values are up counter this value 0 0 0. This we are assuming the k is equal to 1 we have considered. So here we'll get the digital output. So this is Vd which is equal to k into decimal equivalent. And initially this value 0. So this means output of the comparator is 1. This is a AND gate na. AND gate. So here this input is 1. This is the clock. So clock, what is the output will come, you tell me now. So clock only will go na. Output clock will go. So that the counter will get incremented this as 1 like this. Like this the process will be keep on will continue. When you have given this is 1, so what I will get to tell me now here, this is k into d, then now we'll get this value as a 1. So you see the comparator will check the positive terminal voltage, negative terminal voltage. Here analog voltage is how much? 6.2. Digital voltage is 1. Here analog voltage is more now, positive terminal voltage is more compared to negative terminal. So this output will becomes 1. If output is 1, AND gate output is a clock. This clock is given to counter. So the counter will get incremented. So then this value will become 1 0. Like this process will be keep on will continue. Let us consider after some time this output value reaches to a 6, let us say here this is 0 1 1 0. Then how much this Vd value, tell me now here. This is Vd value which will come to be a 6 volts. Now you see still output is 1. This is output is 1 only now. So we'll get the clock, then it will get incremented. So then this value will come to be a 1. Now what is this value, tell me now. Digital value which is a 7. Now this is negative terminal voltage is more compared to positive terminal. So then output will become 0. If this is 0 and clock is applied, that means output is a 0 now. So no clock now. Then there is no clock is given to up counter. So the counter will get stop incrementing. So that is only the output. Now here we have 0. This is 1. This is 1. This is 1. So finally what is this output will come here? V0 which will come to be a 0 1 1 1. Okay. So if you see the maximum conversion time, that depends upon the analog input. So if the analog input which is a more value given, so this conversion time also increases. That is 2 power n minus 1 into t clock. And minimum conversion time is 1 clock. And average means what we can say now? Maximum plus minimum by 2. Maximum plus minimum by 2. That is the average. So how much will come here? That is 2 power n minus 1 plus 1 into t clock by 2. So which will come to be a 2 power n by 2 into t clock. Okay. Here the problem of this counter type ADC is what, tell me now. This conversion time depends upon magnitude of analog input. If the input value is high, then conversion time is also more. And you can see now the resolution of a 4-bit counting type ADC is 0.5. And for an analog input of 6.6 volts, the digital output of ADC is, okay, the resolution is given, okay. Q2, Q1, and that is Q0, and this is analog output. So initially we have taken as first clock. So initially, so this value 0, so this is up counter, so 0, 0, 1. We'll get this value. V0 is what, tell me now? Decimal equivalent into resolution. Resolution is how much? 0.5. So if you multiply, will come with this as a 0.5 will come. Second clock 0, 0, 1, 0. Tell me what I'll get. So will come it as 1. Like this, keep on, will continue. So let us consider we have given, let us say 12 clocks. 12 clocks means this is 1, 1, 0, 0. Na? This value will come it as 6. 13 clocks, 1, 1, 0, 1 will come it as 6.5. Still output is 1. 14th clock, 1, 1, 1, 0. This way is 7 will come. 7 will come, output of the AND comparator is 0. No clock is going. So that means what is the corresponding digital output, you tell me now? 1, 1, 1, 0. This is the digital output. Okay. Next one. SCR, successive approximation type ADC. Successive approximation ADC. So you see this thing. This is one of the fastest. And so here the thing is in this. So here earlier the problem is what will be? It depends upon the magnitude of the analog input. But in case of successive approximation, output does not depend upon the magnitude. It does not depend upon the magnitude. It is independent of the magnitude. Let's see this thing, how it will be independent of the magnitudes. Right. So look at now, what's the process? In this, the working is, if the input to the control logic is 1, agar input to the control logic, if it is 1, then it will maintain the previous bit ko maintain karega. Okay. And if the input to the control logic is 0, then it clears the previous bit. Let's understand this thing. What is the meaning of it? So with one example. Now let us say here we have given an analog input. Let us say an analog input which have given, assume this value given as something. Let us say now here 2 volts we have given. Consider. Now first clock, so we have taken a 4-bit we have considered. So the moment when you have pressed SOC means start of conversion. then it will make this as 1 0 0 0 will make at the starting. Okay, now so this value will be given, this will generate now here. Now you see this thing DAC output voltage we need to see here. So what is this thing here? Digital value, tell me now. Digital value, which is equal to K value, assume it as 1, we have taken a K value. So then this digital value will come it as VD, which is equal to K into D na decimal equivalent, which will come to be a what element now 8 volts. How much this analog voltage, which we have at 2 volts. Now these two are given to comparators. This value, this is VA value given as what tell me now here? This is VA value 2 volts. No? VA value 2 volts and VD value, this is how much given? 8 volts. What is the output of the control logic? You tell me now 0. Output of the control logic is this comparator is 0. So that is going to the control logic. If the input of the control logic is 0, then what happens? If it is 0, what happens? It clears the previous bit. So now this bit is activated now. So since what we have, see this thing by comparison. So since VA is less than VD, then output of this output, which will becomes what tell me now 0, which is equal to 0. Then at the end of this cycle, first clock, it will becomes what tell me now, it will clear this bit ko clear karega 0 0 0 0. Understood this point? Tell me. Okay, next. Next at the second clock, so this value 0. Now this next bit it will make it as 1. Now we'll see this thing. How much the digital value here, which is equal to 4 volts. Analog value how much? Analog value how much? That value 2 volts. It will compare these two here. So VA less than VD. Then what happens now? Output value which is equal to 0. So it will clear this bit also will clear karega. At the end of the second clock, this is 0 0 0 0. In the third clock, what it will do here? This is first bit 0, second bit 0. This bit is 1 and this bit is 0. Here you tell me what will happen. Now what is this VD value? Tell me. So which is at 2 volts. And VA value how much? Which is also 2 volts. Then what is this output? You can see now here. Yes, so then V0. So here VA, so equal to VD na. VA equal to VD. Still this value, output value, which will become 0. So it will clear this bit. So then this value will come to be a 0 0 0 1. If it is greater only 1, comparator, if it is greater only 1, otherwise 0 only. Next here 0 0 0 1. Now you tell me now what is this VD value? VD value 1 volt. VA value how much? Which is 2 volts. By comparison, so this is VA value greater than VD na. So then how much is V0 will come to be a 1. V0 will come to be a 1. So this means what I will get, you tell me now. This is, it will reset. So that it will maintain a bit 0 0 1. So this is an output voltage, corresponding output voltage now. Understood this one? Tell me. Okay. Right. So in this case, what happens now in case of SCR? In case of SCR, conversion time is uniform. Whether it is a small value or big value will maintain as uniform only. And it does not depends upon the magnitude, it depends upon only on the number of bits only. It depends upon conversion time, depends upon number of bits only will depends. Here this magnetic conversion time is how much now? N into T clock. In case of SCR, resolution which is given as V reference by 2 power n minus 1. Yeah, you take this problem. An 8-bit unipolar successive approximation register ADC is used to convert 3.5 volts to digital equivalent output. The reference voltage they given as a +5. Output of ADC at the end of the third clock pulse is. Yes, so understood this problem? Now, first of all, you tell me now, and what is this resolution? Tell me now, K, which is equal to V reference by 2 power n minus 1 will come. V reference is how much? They given as 5 volts, no? This is 5 by, that is 2 power 8 minus 1, which will come to be a 5 by 2 power 8 means 256, that is 255. So which will come to be a 0.019. Okay. Now they are talking about which clock, you tell me now? 3 clock. At the end of the 3 clock. You tell me now working here. First clock, what happens? You tell me now clock 1. Clock 1, what will happen? You see. So this 8-bit now. So this is 1. The MSB bit will be 1. The remaining all bits are zeros only now. This thing, isn't it? Now for this correspondingly we need to get this output now here. What is this V0 value? Tell me now. That is K into decimal equivalent. So how much this value? Tell me now here. K value. So this is 0.019 into decimal equivalent is how much now? This value 2 power 7 now. 2 power 7 means what? Tell me now. 64 128. So how much this value VD will come to be a? Tell me now. Which will come to be a 2.432. Check this thing. And how much the analog value given? 3.5. So that means here analog value greater than digital value. So it will maintain the bit. So this value, so this is at the end of the first clock pulse, this is 1 0 0 0 0 0 0. Okay. Next, tell me the second clock, what happens now? Clock 2. This is 1, 1, 0, 0, 0, 0, 0, 0. You can tell me now what is this VD value? VD value K into D na here. So that is given as K into D. K value 0.019 into D value how much? Decimal equivalent 2 power 7 plus 2 power 6. 2 power 7 plus 2 power 6. How much this value? Tell me now VD value. That is 128 plus 64. So how much will come here? Multiply. This is 3.648. Here what is this VA value? 3.5. So you see this thing here. Here VA value less than VD value. So that means it will clear the bit. So that means it is 1 0 0 0 0 0 0 0 will come. Now at the third clock, what will happen? You see, at the starting of a third clock, this is 1 0 1 0 0 0 0. Yeah, you can see now in this case VD value, how much now here? K into D na. So this value VD will come to be a K value 0.019 into this value, how much now? So this is 2 power 7 plus 2 power 5. So 128 plus 1632. So how much this VD value will come? That is 3.04. How much is VA value? That is 3.5 na. Here VA value greater than VD, right? So that means it will maintain the bit. So this is 1 0 1 0 0 0 0 0. This is the output at the end of the third clock. So you can see the option now here. The option is option A. Okay. Right. And so after this we will have a break for 20 minutes of break. Thereafter we'll continue our class. Then we'll discuss the sequential circuits problems हम discuss करेगा. After the break we'll discuss the sequential circuits problems we'll discuss. Okay. Okay. We are back. We are back. So fine. Hmm. We'll continue the next topics will continue. Fine. We'll do sequential circuits problems. We'll do. Okay. Take this one. Right. Take this problem. The mod number of the counter shown in the figure below is, what is the mod number? The mod number of the counter. So first of all, you tell me now what type of counter is it? Synchronous. So it's a asynchronous counter. First of all, you tell me now what type of counter is it? Synchronous counter, asynchronous counter, you tell me. And first, there is counter which is a asynchronous counter. This is asynchronous counter. And asynchronous counter, up or down counter, you tell me. Up counter, down counter. You see this thing, clock is from the, and here this is a LSB na, and here this is the MSB. Here clock is given from 𝐂𝐤𝐬𝐞, so that means what we can say Q into, it is negative edge na, so this means minus, which is equal to minus Q bar. That means this is in कौन सा स्टेट में आई अभी, दिस इज द दुख में आई ना, दुख के बाद क्या आएगा, यू टेल मी ना, सुख आएगा. दुख के बाद what will come here, sukh will come. So that means this is what counter I can say, up counter. So this is asynchronous, I can say this as up counter. Asynchronous up counter. Okay. Asynchronous up counter. And you can see now clear. So these bubbles are there. Now bubbles will cancel it now here. CLR clear bar. And which is equal to what they given now here. This is Q2 and Q3 given. So this is given as what element of Q2 and this is Q3 bar. So then what will come? CLR, which is equal to what you tell me now here, Q2, this is Q3. Okay. Now you can tell me now Q3. So this value I can arrange in the order now here, CLR. So that is Q3 is MSB. So this is Q2. Q1, Q0 is not given. So means we can say 1 1. So this is 0 0 na. So from this what we can say now, this is mod number from this. So this is a mod number which is equal to 12. This is mod 12 counter. Okay. Next you can tell me now, consider a combination of T and D flip-flops. So connected as shown below. They ask him to find the initial state. So this clock, this is what type of counter you see? Tell me now, synchronous or asynchronous counter? This is synchronous counter, asynchronous counter. This is so same clock now, so synchronous counter. They asking after 4 clock pulses. They asking what will be the value after 4 clock pulses. Now we need to form a table form. We need to form it. Clock. Now you can see now this is my clock, right? So we have a D flip-flop here, and D which is given as what element of Q1 bar given, and then T flip-flop which is given as Q0 is connected. So we'll get it as what element of here? This is Q0 plus and Q1 plus will come. So initial states of the flip-flops are given as what element of 1 1 is the initial state. They are asking after 4 clock pulses. So 1 2 3 4 clock pulse. So Q1 bar, so that is 0. Q0 is 1. So D flip-flop, so output 0. This is 1 means toggle. Next, so Q1 bar, so this is 0, that is 1. Q0 is 0. 1, so 1, this is hold state. 3, so this means Q1 bar is what element of 0. And this is Q0 is what element of 1. This is 0 and this is toggle. 4th clock pulse Q1 bar, which is 1. So it will come to be a 0. So Q0 which is equal to 0. So we'll come it as what element of here? So 0 and this is 1. Zero now, so it is hold state. Yes, so then what's the output? You see this thing here? 0 1. Okay, so you should be careful here. So this order is important. Now here, previously also we got the same thing. So 0 1. Here they asking the order is 1 0 they asking. So this is Q1 Q0. This order we need to give now. Q1 value 1. This is 0. This is the option. Okay. Next. And you can say a T flip-flop can be implemented by using SR flip-flop. Identify the correct implementation. So they are implement T flip-flop by using SR flip-flop. T flip-flop characteristic equation. What is a characteristic equation of T flip-flop? Tell me. That is Q plus, which is equal to what element of Q XOR with T. Okay. Now we need to get this form here. So SR flip-flop is given. So now let's try to implement now here by using SR flip-flop, T flip-flop we have to implement. The characteristic equation of SR flip-flop is what, tell me now? That is S plus R bar into Q. So if I verification of from the options, I am verifying the option B I am considering. So that is S is equal to what, tell me now? S is equal to T, yes, T into Q bar, and R is equal to what, tell me now here? T into Q. So place them here in this equation. So then what will come, the Q plus will come it as T Q bar plus T Q whole bar into Q. So that is Q plus, which is equal to T Q bar plus T bar plus Q bar into Q. So then will come to be a Q plus, which is equal to T Q bar plus T bar into Q. This is 0. So this is Q plus will come it as what, tell me now? T XOR with Q. Okay, so then this is satisfying now, so option B. Here the verification only we need to do it, this type of problem. Consider the circuit shown below. Initially both the flip-flops are cleared. Okay. Now they ask you the number of used states. Used states is indirectly they ask you to find the mod number. Indirectly they ask you to find this mod number. So try this one. Yeah, you tell me now here flip-flop inputs. We have TA. TA connected to what, you tell me now? TA connected to QA, QB. That is QA plus QB. Next, TB connected. What about TB now here? QA bar QB. So this is what element of QA bar plus QB. Now you tell me now, so this is QA plus and QB plus. Now we can say now 0, initially 0, 0 we have taken. So this is 0, this is 1. So we will come it as T flip-flop 0, this is toggle. Now this is 1 and this is 0, this is 1. So toggle and this also toggle. Next 1, so this is QA bar 0. So this value toggle and this is hold state. So the same thing we got now. So this mod number is how much, we can say 3. So this is a mod 3 counter. Okay. Next. In the circuit shown below, initially all the flip-flops are reset. The output Q2, Q1, Q0 after 4 clock pulses is. Here you can see now this is the D flip-flops we can do based upon the block diagram analysis we can do it. Right, so this one. So which we have this as what else now D0, Q1 and this is Q2 we can say now. They has taken the NAND gate they has taken, right? So they took it as a NAND gate like this. They connected like this and this one which is passed to here. And here this is my 𝐂𝐚𝐿𝐾. Okay. Now you can see this thing. What is this working? So that is 𝐂𝐿𝐾 and which is given as what element of here Q0. So Q1 and that is Q2. Yeah, tell me now here initially all the flip-flops are 0, 0, 0 initially. When you apply first clock, so this is a NAND gate between Q1 and Q2 now. Will come it as 1. 1 will come here. 0, 0. Shifting will take place. Next second clock when you apply NAND gate 1, 1. This is 0. And third clock when you apply, so this is the NAND gate that is 1, 1, 1. Fourth clock which is 0, 0. This is 1, 0. And fifth clock, why 0? This is 1. So 0, 0, 1. Sixth clock, 1, 0, 0 will come. Isn't it? So what is mod number you see? So this one, same thing is repeated. So that means if I call this as T1, this is T2. Mod number is 6 minus 1, that is 5. Mod number is 5. Next. The circuit shown consists of a T flip-flop. Each have a clear option as shown in figure. The counter corresponding to the circuit is. And what is counter they are asking to find. So you tell me now first of all asynchronous counter, up or down counter, you see this thing here. Up counter, down counter, Q, this is Q1. Trigger negative. That is what tell me now. So this is minus. We have given a clock is Q, trigger is given minus. So that means we can say minus Q. Minus Q बोले तो अभी कौन सा स्टेट में है, दुख में है ना. So then दुख के बाद what will come here, सुख आएगा. दुख के बाद what will come here, सुख आएगा. Right. So that means we can say each have a clear option as shown. The counter corresponding to the circuit is. Now you can tell me now from this sub counter. So this means which is an up counter. So this is up counter. Up counter means down counter things we can eliminate now. So then clear pin. So then clear bar which is activated when you see. So this is Q2 and this is Q1 whole bar. That means clear pin equal to what terminal here, simply Q2 and Q1. This is nothing. So 1, 1. So this is what terminal 0 now. 1, 1 and this is 0. So that means what I can say in mod 6 up counter. Next. Consider the circuit shown below. The sequence of QA from the first clock is. They are asking the what will the sequence of 𝐂𝐸 will get. And we will form a tabular form. So you can see the inputs now properly. So they given JA equal to what tell me now here QB, and KA equal to what tell me now here QB. Next JB equal to what tell me now QC, and KB equal to what you tell me now here 1. Next JC equal to what tell me now QB bar, KC which is equal to 1. So, and we need what element of QA plus QB plus QC plus. In the first 3 clock pulse we need now. Initially the flip-flops are 0, 0, 0. Now you tell me now first clock what will happen. So this value 0 and 0. 0, this is 1, 1 and this is 1. 0, 0 hold state. 0, 1 reset. 1, 1 toggle. QB, so that is 0, 0. QC 1, 1. QB bar 1, 1. So what will come you can see 0, 0. So this is hold state. 1, 1 is a toggle. 1, 1 is a toggle. Okay. Next QB means 1, 1. QC 1, 1. QB bar 0, this is 1. 1, 1 is a toggle. 1, 1 is a toggle. So 0, 1 is a reset. Next, we have QB value 0, 0. QC value 0, 1. QB bar is 1, 1. 0, 0 reset. The 0, 0 is a hold state. 0, 1 reset, and this is toggle. They are asking to find the QA na. So you see the QA values now we are getting like this na. 0, 0, 1, 1. So check the options now. 0, 0, 1, 1. So option C. Next. A T flip-flop is implemented by using D flip-flop as shown in figure. A T flip-flop is implemented by using D flip-flop. They are asking what will be the logic. They are asking the logic gate is, what should be this logic gate? And the T flip-flop, the characteristic equation is what, tell me? T flip-flop ka characteristic equation, that is Q plus, and which is equal to T XOR with Q, and D flip-flop ka characteristic equation, that is Q plus which is equal to D, right? So now you can tell me now here one input is Q, this is D, so this means this must be a Q T XOR with Q, that means this must be a XOR gate hona padega. So this means which gate you tell me now? XOR gate. Next, the frequency of the pulses at the point D. So this thing. Now tell me now here, if I here this is the F clock. F clock is given as how much now here? 100K. So this is a mod 10. Here this is frequency is a f clock. Output will becomes this a mod 10 mod ring counter modulus mod number is n bit now. So 10 bits. So that's why it will becomes what I can say now here f clock. Here will come it as what I will be f clock by 10. Next here this is mod 20 ripple counter. Mod number directly given. So this means here f clock by this is 10 multiplied by 20. Now parallel counter means synchronous counter. Mod number of parallel counter is 2 power n. So this means here frequency will come to be what, tell me, f clock by 10 into 20 into 16 to power 4 now. And here this is the Johnson counter mod number is 2n. So this will come to be f clock by 10 into 20 into 16 into 2n means what we can say now 8. So what is the output frequency, tell me? F clock, how much now here? 100K. 100 into 1000 by how much now? 10 into 20 into 16 into 8. So simplify, tell me the answer. So these two zeros will get cancelled now here. And so this value 2, this is what will be now 400. So we can say now 8, 4 2s, 4 1s, 4 2s, 5 na 32. So how much will come, you can see, you can check this value, how much now. So this is 125 by 32 na. So how much will come? How much will come, you see? So this is 3.9. Next one. Consider the below edge triggered JK flip-flop. Present output at Q1 Q0 is 0 0. The output for next 3 clocks is. So you can see now. Now you can see now here JK flip-flops. The inputs you can see. J1, which is equal to what will be now here Q0 bar. K1, which is equal to 1. Yes, and J0, which is equal to what, tell me now? So sum of these two is a 1 only now. And K0, which is connected to always 0. So then we'll come it as what, tell me now here? Q1 plus, and this is Q0 plus. Now the present output which is initially cleared. So tell me what will come here. So this value 1 and this value 1. 1 and this value 0. So you tell me now JK flip-flop what will come here. 1 1 is a toggle. 1 0 is a set. They are asking of output after 3 clock pulses we need. Tell me now next one Q0 bar which is equal to 0 and this is 1. 1 and this value 0. So 0 1 will commit as what I will reset now. So this is set. Q0 bar. So Q0 is 1. So this value 0. This is 1. This is 1 0. So this value 0 1 is always in the same state forever. You can see 1 1. Next thereafter 0 1 0 1. Option A. Next. Consider circuit shown in figure 1. The sum output of a off adder is connected as a clock excitation for Johnson counter. Okay. The input waveform at X and Y are shown in figure 2. Initially the output of the counter which is reset. Find the number of state transitions at Q1 over the duration of T. How many transitions happens? We need to see that one. Okay. So that means number of transitions of Q1 they are asking. So this is Q0, this is Q1, this is Q2. Okay, so that means we should talk about this output we need now here. Yeah, you tell me now what is this output will come first of all. And the given sum is given as a clock is given now. So you can talk about when the output is 1. So sum expression which is equal to what, tell me now. That is X XOR Y. You can see now here in this case. When this value 1 we need to talk now here this thing. Now you see this thing here over this time period T we need to find. Yeah, you see this thing here. Whenever these two inputs are different, then output is 1. We need to talk about how many clocks will go. How many times output is 1 we need to see here. Look at now here up to here this value 0 only. In this interval output is 1. And in this interval both are 1. So then output is 0. Again in this interval which is 1. Right. In this interval. Yes, both are 0. So again in this interval this is 1 and this value again which is equal to 1. Like this will go. So you see this thing here. This is the what type of trigger? Rising edge means positive edge trigger. Now you can see now here. This is positive edge 1, 2, 3. This is 4, 5, 6 and 7. So 7 we have at 7 clocks we have. They ask a number of state transition. They ask you 7 clocks are there and you can see now this is Q2 and this is Q1 and that is Q0. So how many transition? Transition means number of changes. You can see now here this value initially, this is what counter? This is Johnson counter now. So this value initially all the states are zeros. So 0, 0, 0. Next will come it as 1, 0, 0. Next 1, 1, 0. Next 1, 1, 1. 0, 1, 1. 0, 0, 1. How many? 7 clocks. 1, 2, 3, 4, 5, 6, 7. So 0, 0, 0. Okay. Yeah, they are asking to find how many times the Q1 will have a transition. So you see, tell me how many transitions are there? Change now here. Initially up to here, this is 1. Here we have one transition. 1. Again here same thing. Here we have another transition. Same thing. So how many transitions? You can see now changes we have. Like we sense a control system number of sign changes now. Same thing, number of state transition we need to see here, which is equal to 2. Okay. Next, initial content of the below shown 4-bit shift register is given. They are asking to find what will be the number of clocks required to get the same content in the register once again. How many clocks required? I have to get back the same content again. Let's see how many clocks required to get back the same content again. So here this is clock. And if I call this as Q3, Q2, Q1, this is Q0. So this is Q3, Q2, Q1, and that is Q0. So you can tell me now here initially. So here we have 0, 1, 1, 1. This is the initial state. And they given this as what is this thing input, you tell me going here. The input which is going here and which is equal to, this is Q1, Q3. So this is Q3 XOR with Q0. Now you can tell me what will come. XOR between Q3 and Q0. Q3 and Q0 XOR. So first clock when you apply, this is 1. So 0, 1, 1. Second clock XOR is 0, 1, 0, 1. Next third clock 1, 0, 1, 0. Fourth clock, so this is 1, 1, 0, 1. Fifth clock 0, 1, 1, 0. Sixth clock 0, 0, 1, 1. Seventh clock 1, 0. So this 1, 0, 0, 1. Eighth clock 0, 1, 0, 0. Ninth clock 0, 0, 1, 0. 10th clock 0, 0, 0, 1. 11th clock, this is 1, 0, 0, 0. What here? We are not getting. 12th clock, so this is 1, 1, 0, 0. 13, 1, 1, 1, 0. 14, 1, 1, 1, 1. 15, 0, 1, 1, 1. Yeah, 15 clocks. Check it, all of you. Everybody got the same thing. 15 clocks we got. Hmm? Next, and frequency of this output. Now here we have f clock, and then we'll find it as what will be now here 10-bit ring counter. So we'll come it as ring counter. Now mod number is n only. 10-bit means f clock by 10. Parallel counter, this synchronous counter. So this means how much? F clock by 10 into 16. Next here, what will come here? F clock by, so this is 10 into 25 into 16. And Johnson counter mod number is 2n. So this is 10 into 25 into 16 into 8. So how much the frequency, tell me? Output frequency will come it as input frequency 160 given. 160 kilo now, that is 1000 by how much now here? 10 into 25 into 16 into 8. So check for cancellations now here. 16, this 160 will get cancelled. 25, 4 into 0. 8 5s now. So that's why 5h. Next, consider the partial implementation of a 3-bit mod 8 up counter shown below. To complete the circuit input X should be X value they are asking. We need to design it. Now you tell me now here. So we need to get it as what? A 3-bit mod 8 up counter. We need present state, next state, so this is Q2 and this is Q1 and this is Q0. This is the present state. Next state is what will be now? We can say Q2 plus Q1 plus and Q0 plus. This is the next state, and we need to write the flip-flop inputs. Flip-flop inputs we should get. And so then here we have T flip-flop now, so that is T2. T2, T1, and this is T0. Okay, you can see now up counter now. So initially 0, 0, 0. If I say next state is 0, 0, 1. 0, 0, 1 is a present state. 0, 1, 0 is a next state. 0, 1, 0 is a next state. 0, 1, 1, 3. 3, 4 is a next state now here. And 4 is a present state. Then 5 is a next state. 5 is a present state. Then 6 is a next state. And 6 is the present state, 7 is a next state. 7 is a present state, then 8 is, 0 is a next state. Then we need to match it now here. T flip-flop का character excitation equation we know now. As we know here, Q plus, which is equal to T XR Q. From this, T is equal to what we can say now here, Q plus XR with Q. Now let us see this thing. Tell me now what will come. Now here, so XR 0, 0 XR. We need to get this only. Now major will focus here 0. So 0, 0, 0 XR 0, 0, 0. 0, 1 is 1. 1, 1. So that is 0. 1, 1. So 0. 1, 1, 0. 1, 0, 1. So what I will get, you tell me now T2, which will come to be a, the min terms, you see this thing, these are the term, these are the one other term. So we can write it as, what tell me now in this case, so this is Q2 bar, so that is Q1, Q0 plus, this is Q2, Q1, this is Q0. So if I have taken the Q1, Q0 common, so this will be Q1, Q0. So option C. Check this one. Next, the frequency at the output of the following cascade circuit is. Here, this is the clock frequency, ring counter, modern. So this means F clock by 10. Here, mod 60 in given. So means we can say F clock by, so 10 into 16. And this is Johnson counter 2n. So that is F clock by 10 into 16 into 10. So then how much is output finally? So 200. So this is 200 by, so this is 100 into 16. So I will get cancelled now. This is 1 by 8. Will come how much now here? 4.125 now. 0.125 kilo. If I want H means what are now 125. Correct only now? Next. Consider the sequential circuit shown below. The output Z becomes 1 after every n clock cycles. The value of n is. The value of n is. That means indirectly they are asking to find what terminal mod number they are asking to find. Consider the sequential circuit shown below. The output Z becomes 1 after every n clock cycles. The value of n is. Okay. After every n clock cycles, right? So we need to get the output now here. So tell me now tabular form. We need to find the mod number, right? So first we have a J0. So this is J0 is given as 1 and K0 is given as, that is also given as 1 only. Next J1. J1 which is given as what element of Q2 bar, and K1 which is given as 1, and this J2 given as what element of, which is equal to Q1 bar, Q1, and K2 given as what element of here, that is which is equal to 1. So so here J0 which is given as 1, K0 is also given as 1 only. Next we have J1. J1 is given as Q2 bar, and the K1 is given as what element of 1 only. Next J2 given as what element of here, which is given as Q1, K2 given as 1. Then we have here, so this is Q0 plus Q1 plus, and this is Q2 plus. Now complete it. So sequential circuit problem solving, you need to have a full of patience is required. So you can tell me now first 1 1. Both are 1 1. So this is initial values are 0 0 0. This value 1 1. So this value 0 1. 1 1 toggle. 1 1 toggle. 0 1 is reset. Next, so this is 1 1. So Q2 bar which is equal to 1. So this is 1. Q1 which is equal to 1 1. So toggle, and this is toggle, this is toggle. And Z is equal to, we should have Z value becomes 1 means this value 1, this value 1, this value 1. Mean this value 0, this value 0, this value 0. Indirectly we should find mod number. Okay. So this is again 1 1. So Q2 bar, so this is 1, sorry 0. This is 1. Q1 is 0. This is 1. 1 1 toggle. 0 1 reset. 0 1 is reset. Next 1 1. 1 1. So Q2 bar which is equal to 1 1. Q1 which is equal to 0. This is 1. 1 1 is toggle. Toggle. Toggle means this is 1. This is reset. Now next 1 1. Tell me now here Q2 bar. Q2 bar is 1. K1. This is Q1 which is 1 1. So toggle. This is toggle. This also toggle. Next we have 1 1. This is Q2 bar. Q2 bar. This is 1. So 0 1. Q1 is 0, this is 1. 1 1 toggle. 0 1 reset. 0 1 reset. Yes. 1 2 3 4 5 6. 6 clocks. Next. A 2 MHz clock signal is applied to JK flip-flop with J is equal to K equal to 1. The frequency of output signal of the flip-flop is equal to the frequency the frequency of output signal of the flip-flop is equal to. So J is equal to 1, K is equal to 1. That means that is nothing but toggle mode now. In toggle mode, what we can say? So frequency given as clock frequency given which is equal to 2 mega given. Now what is the output frequency? Tell me now here. So this is the mod f clock by mod number. Mod is after 1 clock pulse 2. This is the mod number now. Only one flip flop, that is mod is 2. Will come it as 1 mega. But they ask in terms of kilo now. So that's why what is the answer? You tell me now here 1000 kilo. Next. For the given connection, if the initial state of Q1 is 1, Q2 is 0. The output frequency in kilohertz is output frequency. So first of all, we need to find the mod number. So tell me this mod number in this case. And you can see now here D1. So D1 which is given us, what tell me now here, D1 which is connected to Q2. Okay. And then D2, and the D2 which is given us, what tell me now here, which is equal to Q1 bar. And we have, this is Q1 plus and this is Q2 plus. They ask you to find this frequency means mod number. This is initial value 10. 10. So you can tell me now here Q2 which is equal to 0. So this is 0. Initial value which will come it as 0 and 0. Next clock. So Q2 which is equal to 0. D1 is equal to Q2, D2 equal to Q1 bar. Okay. Initial value 10, D1, Q2 value 0. This is okay. This is always getting 0 only, no? Always we are getting 0 only, isn't it? D flip flop. Isn't it? See the circuit now here. D1 is equal to Q2. Okay. D2 equal to Q1 bar. Yes. And Q1 plus 1 and this is 0. Yes, correct only. Okay, Q1 bar means 0, so this is 1. Okay, sorry. So 0, then it is 0 only, and this is 1. Q2, this is 1. Q1 bar, so this is 1, so this is 1 and 1. Next Q2, so this is 1 and 0, so this is 1, will come it as 0. Next it is, what, tell me? We have Q2 0, Q1 bar 0. Now it is 0 0. Yes, here only we got the same thing, same state now. 1 2 3 4, 4 clocks. So this mod number is 4. Mod is 4. So then output frequency synchronous counter, everywhere output frequency remains same only. So which we have 1 mega. So this means, yes, kilo I can write. 1000 kilo. 1000 kilo by 4. How much you can say now? This is 125 kilohertz. Right. Next. Try this one. Yes. Consider the circuit shown below. They ask him to find the values of Q2, Q1, Q0 after first clock pulse is equal to. After first clock pulse. After applying a first clock pulse, what will be the values? Initially, the values are given as 0. So, this value 0. Initially, this value 0. And this value 0, this value 0. Okay. Yes, so this value 0. That means this is 1, this is 1, and so fine. This value will go to here, this value here. This value will come here. So this is 0, this is 1. Okay. Next, this is 0, this is 1. Next, after one clock pulse, what happens? We have given 1 0, that is this value. Q2 value will come it as 1 0 1. So that is reset na. Q1 value 0. So this is Q0 value reset. So this is 0. So it will come 1 0 0 will come. Next, a 3-bit triple counter is to be designed as mod 4 counter. We need to design this as a mod 4 counter. For this, what is the best architecture of the logic gate? Now, so tell me, we need to design mod 4 counter. For mod 4 counter के लिए, they given from weight they given now here Q2 say they given. For mod 4 up counter, so you can see now when we got it as, when a clear pin we need to activate, you tell me now here. That is at 1 0 0 we need to activate. So this is Q4. The moment this is 1, so if I connect like this, we can clear pin will get active now here. So that means, do you need any logic gate? No logic gate is required, simply wire connection. Simply wire connection. So yeah, कोई प्रॉब्लम नहीं है, हम हिंदी भी यूज करेगा. सो आपने समझना पड़ेगा थोड़ा मेहनत. तो सिंपल लैंग्वेज हिंदी इंग्लिश दोनों इस्तेमाल करेगा, बट लेकिन सो सिंपल सरल लैंग्वेज हम यूज करेगा. ठीक है, समझने के लिए कोशिश करो. अगर वरना सो हियर यू कैन आस्क मी. Right, a 4-bit synchronous up counter is holding the state. What will be the count after 27th clock pulse? 27th clock pulse के बाद कितना होगा? अभी initially, so the state at the 0th clock, The state is how much? You tell me now. 0 1 0 1. So 4 bit now. For every 16 clock pulse will repeat again. So 16th clock में क्या आएगा? You tell me now here. Same आएगा. So 0 1 0 1 will come. 16 इसके बाद वापस 32 में आएगा. 32 में वापस again will come it as 0 1 0 1 will come, isn't it? But लेकिन हमको 27th clock pulse में चाहिए ना. So means here 32 से हमने back पीछे जाना पड़ेगा. Means what we have? This is 27 28 29 30 31 32. A 32 पर this is 0 1 0 1. So this means which is equal to what element of 5. So अभी इधर क्या आएगा? इधर you tell me now 4. इधर will come 3. This is 2. This is 1. And here we have a 0. Means 0 0 0. Next, the following synchronous sequential circuit has dash number of state. That means indirectly क्या पूछ रहा है इधर? Mod number. We need to find the mod number. We need to find. So tell me now mod number के लिए. So we have a J0. J0 is given as what? Tell me now. Q1 bar. J0 is given as Q1 bar. And K0 is given as what? Tell me now. 1. And here J1 is given as what? Tell me now. Q0. And K1 is given as what? Tell me now. That is 1. So we have, and thereafter we have this as what? Tell me now here. Q0 plus, and this is Q1 plus. Okay. So we need to find this mod number for it. So tell me now here mod number के लिए. So initially 0 0 मान लीजिए. Now tell me now here. So Q1 bar. So which will come it as 0 na. So 0. So this is 1. This is 1. Here tell me now here 1 1. So this is 0. This is 1. 1 1 will come it as toggle. 0 1 will come it as reset. And so this value Q1 bar which is 1, this is 1. Q0 which is equal to 1, this is 1. So 1 1 is a toggle. 1 1 is a toggle. So now you can see now here Q0, Q1 bar, J0 which is equal to Q1 bar is 0, this is 1. Q0 0, this is 1. 0 1 reset, 0 1 reset. So this mod number is 3 na. So this mod number which is equal to 3. Next. How many flip-flops would be complemented in 10-bit ripple up counter to reach the next count after the count is this much? So they given this count as what? Tell me now. 1 0 0 1 1 0 0 1 1 1. This is the initial state. So here they are saying it is up counter. Up counter के लिए what the next state will come? You tell me now. Next state is 1 0 0 1 1 0 1 0 0 0. You see this thing? These 4 flip-flops are complemented. You see? So these 4 flip-flops are complemented. How many flip-flops will changes its state? You tell me now here. Number of flip-flops are 4 flip-flops are complemented. right? Next, now this matched with the respect to characteristic equation. So then, yes, SR flip-flop characteristic equation, S plus R bar into Q. So this is what element of 2 now? And JK flip-flop. So this is what element of JQ bar plus K bar into Q. So this is a 4. And D flip-flop, which is equal to Q plus is equal to D only. So this is a third one. And T flip-flop. So this is T. So that is 7. So you can see now here 2, 4, 3, 7. Option D. Next one. The average propagation delay of each NAND gate in the clock generator circuit is 10 nanosecond. The frequency of the signal at Q0 is. The frequency they are asking to find now. So you can tell me in this case. And first of all, you see this thing, this is nothing but Johnson counter. Johnson counter mod number is how much? 2n. Johnson counter mod number is 2n. So you can see now here the time frequency synchronous counter frequency at each case is same only. Each flip-flop is same only. So the time period, so that means T clock, that must be greater than of delay. So average propagation delay they given. So this should be greater than what we can say now here. So this is 2n into TPD. 2n into TPD. Now, so you can simplify it now. We need to find T clock. So this means we can say 1 by F clock. That must be greater than 2 into n value. 1, 2, 3, 4, 5 are there. 5 NOT gates. Into TPD given 10. So 10 into 10 power minus 9. So you can tell me now here how much will come F clock. F clock. So it should be less than what I can say 10. So this 10 power minus 7. This is will come it as 1 by 10 power minus 7. So I can say this as from this F clock it should be equal to 10 mega. 10 megahertz. Isn't it? Completed. Fine. Right. Okay, fine. Yeah, that's it for today's sessions. In the next session, we'll meet up. We'll complete the remaining analysis. Fine. Okay, then. See you. Bye bye.